Chemists are always looking to understand molecules and bonding better. One tool that we can use to help us understand molecules better is hybridization. And this is where we're going to take atomic orbitals and we are actually going to mix them. Again, all in an effort to understand bonding and reactivity of molecules better. Let's get started. Ultimately, we want to use hybridization to predict molecule reactivity. Are bonds going to form? Are bonds going to break? So remember, all of this bond formation and bond breaking is related to where the electrons are. So if we can know where the electrons are in a molecule, this gives us a very powerful tool to predict reactivity. So hybridization is going to help us predict geometry. Now, specifically, hybridization is going to predict what we call electronic geometry, as opposed to VSEPR, which helps us predict molecular geometry. But still, we're trying to figure out where the electrons are so we can predict reactivity of molecules. So we have multiple atomic orbitals that we can mix. We are going to start with mixing one s orbital, which of course is a sphere, and one p orbital. Now in this case, we are mixing the px orbital because you can see this is along the x-axis. Now, when you mix these orbitals, you get characteristics of both. So you end up with orbitals that look like these two right here. Now, there are a couple of things that I want to point out. Your number of orbitals is going to be conserved. So we mixed one s and one p. We mixed two different orbitals. So we are going to get two hybridized orbitals. Because we mixed the px here with the s, our hybridized orbitals are along the x-axis right here. Now, in terms of geometry, when we put these two orbitals together, you can see in this picture here, what we get is a linear arrangement. These two orbitals are 180 degrees from each other. Now, the one thing that this picture doesn't show, because it makes it really complex, is you do have these smaller lobes. They're really kind of embedded here within these larger lobes, which is why we don't actually bother to show them. But they are still there. They haven't disappeared. These two new hybrid orbitals are called sp hybrid orbitals. Again, there are two of them because we mixed one s orbital with one p orbital. Now let's see what happens when we add more than one p orbital. Now we are going to take one of our s orbitals and we're going to mix it with two different p orbitals. So again, we've got the px here, it's along the x-axis, and the py along the y-axis. Remember, your number of orbitals is conserved. So we have mixed 1, 2, 3 atomic orbitals. So we are going to get 1, 2, 3 hybrid orbitals. Just like with the sp orbitals, we want to put these three orbitals together and see what the geometry is. And when we do that, we get this geometry right here. The lobes are 120 degrees apart. This is trigonal planar. Again, the little lobes are embedded within here. They don't just disappear. It just makes that picture really complex. And of course, the electrons spend most of their time in the larger lobes, not in the little lobes. So when we mix our one s orbital with two p orbitals, we are going to get 3 sp2 hybrid orbitals. Now let's see what happens when we mix our s orbital with all 3 p orbitals. Okay, so here is our s orbital, and again we have px, py, and pz. So these are all 3 of our different p orbitals. Just like before, our number of orbitals is conserved. So we have mixed 1, 2, 3, 4 atomic orbitals, and we are going to get 1, 2, 3, 4 hybrid orbitals. And you can see these hybrid orbitals are oriented along different axes here. So again, the crux of the question is what happens when all of these orbitals come together? What is the geometry? And this gives the tetrahedral arrangement. Again, embedded in here are the smaller lobes, but I won't make the picture any more complex than it is. So this hybridization gives us 4 sp3 hybrid orbitals. So this is great for visualizing how the orbitals mix, what the hybrid orbitals look like, how they're arranged in 3D space. But how do we transfer this to actual molecules? We have a couple of steps to help us determine hybridization on atoms in molecules. Step 1, we're going to count the number of atoms attached to whatever atom we're trying to determine hybridization on. This is our value A. Then we're going to count the number of lone pairs that are on the atom in question. We'll call this L. Our number of hybrids, which we call H, is simply A plus L. Now, when H equals 4, we have the sp3 hybrid orbitals. This again gives us our tetrahedral geometry like we just saw. When H equals 3, this is an sp2 hybrid atom. Again, it gives us our trigonal planar geometry. And when H equals 2, that gives us our sp hybrid orbitals, and this is our linear geometry. I'm going to draw a couple of Lewis structures, and we are going to determine hybridization on the atoms. Let's look at methane. So methane is 1 carbon with 4 hydrogens. Let's determine the hybridization on that carbon atom. All right, so our step 1, we need to count the number of atoms attached to that carbon. Well, there are 4 hydrogens, so our A equals 4. Step 2 is we need to count the number of lone pairs on that atom. Well, that carbon has no lone pairs, so L equals 0. So our value of H is simply 4 plus 0, which equals 4. And when H equals 4, this is an sp3 hybridized carbon. Its geometry is tetrahedral. Let's do another example. Let's take a look at formaldehyde. This is a carbon double bonded to an oxygen with 2 lone pairs and with 2 hydrogen atoms. Again, let's determine the hybridization on that carbon. Okay, our value for A. This is how many atoms that are attached to this carbon, and I have 2 hydrogen atoms and 1 oxygen atom, so A equals 3. I need to count my number of lone pairs on that carbon. This is where students can get a little bit mixed up. You want to look at the lone pairs on the atom in question. Well, I am looking at carbon. Carbon has 0 lone pairs. It's very easy to see the lone pairs up here on oxygen and start counting those, but you want to be really careful that you stay focused on the atom that you're trying to determine the hybridization of. So in this case, L equals 0. Which means my value of H is simply 3 plus 0, which gives me an H of 3. So when my H equals 3, you can see from my table up here, H equals 3, I have an sp2 hybridized carbon, and it has trigonal planar geometry. So you can already see just in these 2 examples, atoms will change their hybridization based on how they're bonded. So you couldn't say, oh, carbon is always sp3 hybridized, because sometimes it is and sometimes it isn't. So you really need to make sure that you are applying these rules and not just going by what the atom is. Let's do one more example. Sticking with our carbon-based molecules, let's do carbon dioxide. Of course, carbon dioxide is double bonded to 2 oxygens here. Again, focusing in on the carbon. The number of atoms attached, or my value for A equals 2. My number of lone pairs, again, on the carbon, not on the oxygens, on the carbon is 0. So my value of H is 2 plus 0, which equals 2. This is sp hybridized, which is a linear geometry. Knowing our geometry and how molecules are put together is going to help us predict reactivity of molecules because we know where those electrons are. So the steps to determine hybridization are really pretty simple, but again, the most common mistakes are students counting lone pairs that are not on the atom that they are trying to determine hybridization. So just watch for that. I hope you have a better understanding of hybridization, and thanks so much for watching.